All right, hello everyone. So today we have the following problem solved by variation of parameters, the equation y triple prime minus 5y double prime minus 9y prime plus 45y equals 7x e to the x. So we have a third order differential equation here, a constant coefficient. And what we're going to first do before we begin variation of parameters is to find the systems to the solutions to the homogeneous equation. So we're going to take that whole left-hand side of the equation, set it equal to 0, and you'd solve. So hopefully you already went over that. If not, then I go ahead and review that. And the key here is to let y equals e to the rx and using factor by grouping. And you would get the solutions y1 equals e to the 5x, y2 equals e to the 3x, and y3 equals e to the minus 3x. And variation of parameters basically states that if you have an equation that's on the form of what you see here with number 1, which is what I had originally up here, we are going to look for a solution of the form that you see here. So your solution y is y1 u1 plus y2 u2 plus y3 u3. y1, y2, and y3 are those solutions to the homogeneous equation, and u1, u2, and u3 are functions of x. And what happens is, long story short, all your functions and their accompanying derivatives need to solve the system of equations right here. Okay, so notice how I have my variables here are u1 prime, u2 prime, and u3 prime. Yeah, as I said, I need to figure out u1, u2, and u3. I said last time, but for me to, but there's a kind of like a middleman here, which is u1 prime, u2 prime, and u3 prime that I have to solve for first. That's just the way it is. It's just the theory. Okay, so you can rewrite that whole box that I have in red as a product of two matrices, where that's like, think of this as A, like my coefficient matrix, and this would be like my X, my matrix that contains my variables that I'm trying to solve for, and B, which is basically, it's always like a column of zeros, the last entry, which is the function here that you're setting equal to. So it's in our case, the 7x e to the x is what goes down there. All right. So, and these are, by the way, these are just the things that I just talked about. They're important in terms of why we're doing what we're doing, but in terms of the computation, this is what you really need. So I'm going to solve for u1 prime, u2 prime, and u3 prime, and I'm going to use something called Cramer's rule. And Cramer's rule is basically taking quotients of determinants. And so here's u1 prime, u2 prime, and u3 prime. And if you take a look at all of these, and if the question here is, what do they all have in common? They all have in common this right here, which is this determinant, which is what we call the Wronskian. And the Wronskian, in so many words, is, so you have a set of solutions, or in fact, it doesn't have to be solutions, but it can be like just any functions. But in our case, we're going to take our three solutions to the homogeneous equation, and what we're going to do is we're going to take two more derivatives. We're going to take two derivatives. Excuse me. The first derivative goes under the original, and the second derivative goes under the first derivative. Okay, and yeah, you're forming like this matrix, which we're going to take a determinant. That's what the Wronskian is. And yeah, if I had 4 functions, then I would have 4 derivatives. So you need to have, for your determinant, whatever number of functions you have, you need to have that same number of rows and columns. So 3 rows, 3 columns. And essentially the way you do that is by taking n minus 1 derivatives. So if I had 4 functions, I would take 3 derivatives to make that matrix. I hope you already saw the Wronskian, but if you haven't, that's how this works. And for each of u1 prime, u2 prime, u3 prime, you have the determinant that's on the numerator, and they're all different here. Taking a look at that, they're all different. Now I'm going to concentrate today on solving for u1 prime, and I'll let you solve for u2 prime and u3 prime. But you can attack this in a similar manner. When you're setting up the matrix on the determinant on the numerator, the way it works is based on this index, that column will get replaced by 0, 0, f of x. Okay, so it's this value that we had up here, b in red. So my first column would be replaced by 0, 0, f of x, and the two other columns stay the same. You might say, what are you referring to? I'm referring to the Wronskian. So it's like this column gets replaced with 0, 0, f of x, and these two columns stay the same. And real quick for u2 prime, what would happen is that the second column in the Wronskian gets replaced by 0, 0, f of x, and the two other columns, the first and the third, they stay the same. So we're going to take those determinants, and if you need to, I would take a second here to try to take the determinant, see if you agree with what I get here. So what I'm going to begin is by solving for the Wronskian. So I plug in my three homogeneous solutions, e to the 5x, e to the 3x, e to the minus 3x. Take one derivative of each and put that result under e to the 5x, e to the 3x, e to the minus 3x, and then take a second derivative. And what I did from here to here was I used some row operations that we're allowed to use to find determinants. We have a rule that says if you multiply a row and then add it to another row, it doesn't affect the sign of the determinant. So that's what I did here in terms of making things a little easier for me. And then at the end of the day, I got, when I did the determinant by expanding by the first column, okay, you get minus 96 e to the 5x. And I would review determinants, of course, if you need to. And then similarly, if you take the determinant d1, you would get this. And d1 here, sorry, I don't know if I noted that. That's just the determinant of this right here. That's what I'm calling d1. Okay. So I took d1, and that came out to be minus 42x e to the x. And all you do is you take your results and you simplify, and this comes out to be 7/16 x e to the minus 4x. And you would go ahead and integrate that. And which method do we use for integration? Well, that all depends on what you have left. In this case, you would use integration by parts, and you would form u1. And similarly, you would form u2 and u3. Okay, so you have u3 right here. And don't forget to add a constant to all of these here. And right here for u1. And essentially what you would do next is you would form your solution, which I said was equal to y1 u1 plus y2 u2 plus y3 u3. And that's what you see here in the blue, red, and gold color there. And if you went ahead and distributed, and that's how I got this answer, I distributed and then I added like terms, so some algebra that you got to do, this would be your final answer. And essentially this right here is the solution to the homogeneous, and this is the solution to the particular. And I mentioned that because you might have already gone over undetermined coefficients, and often the solutions are written out in that way. You have a particular and a homogeneous solution. Well, that you get the same thing here. So you could obviously have used the method of undetermined coefficients as well here. However, that would be a little longer in my opinion. I'd rather use this, even though it's not easy. But I just want to let you make a video on how you would approach this. So basically, you need to know how to use determinants and derivatives and integrate. Okay. All right. Well, thank you for your time. Appreciate it, and I hope this helps.